Systemic interventions and their leverage is based on Donella Meadows' hierarchy of systemic interventions. In this video, we're going to be looking at the range of interventions that are available and asking the question, do different interventions have different leverage for systemic change? Let's consider ways that you can intervene in a system. We begin by recalling Aristotle's model of causality, with each quadrant representing a different causality. As covered in the video on Aristotle's model of causality, the bottom half of this diagram represents the physical domain, or material reality. So what types of interventions can one implement in the material reality? Let's first choose a systemic problem. Let's take ourselves back to 1970, when farming in the US was becoming less popular as a career path, and it was becoming more lucrative to convert farmland to non-farming uses. What are interventions that could take place? Within the natural capital domain, one could increase the area of farmland. That falls in the category of altering numbers, stocks, and flows. While that may temporarily provide more food, it does little to change the prospects of farming as a career. What about changing system rules? Another intervention could be around system rules. This is the intervention that was chosen to create federal government subsidies for farming commodities. Another intervention might be at the level of changing who has access to what information. An intervention at this level could have been an information campaign that brought together the information on how farming represented a stable career path, along with how to enter the farming occupation and get access to the needed resources. Another intervention could have been along lines of empowering self-organization. An example of that could have been regional hosted meetings where commodity farmers met and worked together to make clear their current challenges and address those together. An additional intervention could have been in redefining goals. At this level, one might begin to ask questions about the food system. What was the relationship of industrial commodity farming to a stable food supply? Is the goal of stabilizing industrial commodity farming equivalent to the goal of ensuring that the U.S. could feed its people? As a final area of intervention, we could have questioned our paradigms within our intent. What were they? One was a paradigm of economy of scale, where there is a cost savings when something is manufactured at large scale. If we looked at this paradigm, we could have seen that there is also a cost to the economy of scale model of farming. Centralized farming embeds the need for a shipping system to all parts of the country, embedding a great deal of petroleum in the food chain. Was this the best approach? Are there other models of regional food systems that could have been encouraged instead of centralized industrial farming? So these levels of interventions, mapped against Aristotle's model of causality, are not equal in their impact. These intervention levels, proposed by Donella Meadows, have a hierarchy in terms of their impact. In this diagram, the leverage of the impact is represented by the size of the dot. Let's look at these in a different way. In this figure, the intervention levels are laid out on a lever arm to emphasize the fact that the intervention levels have different leverages. As can be seen, the highest leverage resides in transcending paradigms. The lowest leverage is in the material domain. As an example, consider the sinking of the Titanic ship. There's a famous reference to rearranging the deck chairs on the Titanic. This aphorism refers to the fact that the material changes do little to change the systemic conditions. The act of moving from the material cause to the final cause is equivalent to expanding the boundaries of the problem to include more opportunities for interventions. Within the material cause, the opportunities are material things. Expanding the boundaries to include efficient cause or processes includes processes. Expanding it to include formal cause includes system goals. Further expanding to consider final cause begins to ask questions about our relationship to the problem that is trying to be fixed.
According to Wikipedia, emergence is conceived as a process whereby larger entities, patterns, and regularities arise through interactions among smaller or simpler entities that themselves do not exhibit such properties. In the previous section, we discussed how synergistic relations give rise to the phenomena of two or more elements having a greater combined output or effect than the simple product of each in isolation. This process, whereby the interaction between elements gives rise to something that is greater than the sum of their parts, is called emergence. So, whereas when we were talking about synergies, we simply said that the combined effect was greater than its parts in isolation. The concept of emergence, though, implies that what is created out of these synergistic relations is not just quantitatively different, it is in fact qualitatively different. That is to say, none of the elements that contribute to the emergence of this new phenomena have its qualities when taken in isolation. There are many examples of this, but maybe the simplest is the example of water. Water is made up of hydrogen and oxygen atoms. Neither of these two elements that make up the system have the property or quality of wetness, but when we combine them, we get a substance called water that has the quality of being wet. This property of wetness has emerged out of the interaction of the system's elements, and it only exists on the system's level. Another often cited example of emergence is the phenomena of life. Biological systems, such as a plant cell, consist of a set of inanimate molecules, none of which in isolation have the property of life, but it is the particular way that these elements are arranged into structures and processes that enable the emergent phenomena of the living system as an entirety. Our world is full of examples of emergence that we could cite, from ant colonies to galaxies and cultures, but all of these are types of structures, whereas emergence is really a process. These systems are then the product of a process of emergence that has played out to create two qualitatively different levels to the system. Emergence, then, is a process through which systems develop, or we might say, grow. During this process, unassociated elements interact, synchronize to form synergies, and out of this emerges some new and novel phenomena that previously did not exist. In order to create some qualitatively different and new phenomena, the system must go through what we call a phase transition. A phase transition is an often rapid or accelerated period during the process of a system's development, either side of which the fundamental parameters with which we describe the system can change qualitatively. Again, there are lots of examples of this, such as the phase transition between solid and liquid that a substance goes through when heated, but maybe the most dramatic example is the metamorphosis of a butterfly, from being a caterpillar to a mature adult. Not only does the system's morphology change, but the whole set of parameters that we define it with are so drastically altered prior and post the phase transition that we give the creature a whole new name. This illustration helps to bring us to another important theme within emergence, that is the distinction between what is called strong and weak emergence. Weak emergence describes how the emergent phenomena can be traced back to the individual elements, meaning we can predict and observe higher-level emergent phenomena just by looking at individual components. In contrast, strong emergence, also known as irreducible emergence, states that these phenomena cannot be reduced to the individual components. Instead, the emergent phenomena are traced back to the interactions between the multiple components, so, quite literally, cannot be predicted in any